So Dr. Stephen Wheeler has served as principal consultant for several of the largest computing consulting companies, including Capgemini America, Decision Consultants, and Wipro. More recently, he has worked as a data scientist on the Lockheed Martin Aeronautics Advanced Analytics team, performing advanced analytics on the F-35 Joint Strike Fighter. He is also a FAA licensed commercial pilot with an instrument rating and serves as transport mission pilot with Texas Wing Group 3 of the United States Air Force Auxiliary with the rank of captain. He has successfully completed the Squadron Leadership School and is the Aerospace Education Officer of his squadron. Dr. Wheeler is also a NASA field research astronaut serving as mission commander of NASA's MDRS Crew 88 at the Mars Desert Research Station in Utah. Today, Dr. Wheeler is an information science professor here at the College of Information with research interests in autonomous systems, machine learning, dynamic planning systems, linear symbolic problem-solving systems, and natural language processing. So we invite you to connect with Dr. Wheeler on LinkedIn if you'd like to follow up with him or ask any questions after this conversation. And I've just posted that link in the chat. So welcome, Dr. Wheeler, and thank you for your time today. We are recording this session, so if you'd like to mute your microphones and turn your videos off, this would be a great time to do so. And then please post any questions you have for Dr. Wheeler in the chat, and we'll get to these at the end of the presentation. So without further ado, over to you, Dr. Wheeler.
All right, thank you, Sandy, for that introduction. And we were, as a crew for NASA, in the desert region of Utah, in a research station, which was MDRS, standing for Mars Desert Research Station, from January of 9th of 2010 to January 22nd of 2010. And so this is, there are a few slides that I'll go through, and this is where the research station is located in Utah, not far from the Glen Canyon National Recreation Center. And it's a habitat that is very similar to what will be on the planet Mars when NASA, in collaboration with the European Space Agency, ESA, which is an analog of NASA that the Europeans operate. When this journey happens, there will probably be many different nations, just as in the International Space Station, there are many nations that participate. There may be other nations on this journey to Mars. Now, because of the length of the journey, about 9 months to reach Mars from Earth, it requires that everyone in a simulation determine what problems or what factors are important so to guide the eventual trip to Mars. So we had various research domains that we were specifically assigned. I was assigned as a crew commander and also as a micropaleontology expert. So the members of our crew each had a research assignment. Mine was paleontology, and Diego Urbana was biology. And we'll talk about more of the crew members as we get to that in just a moment. So this is where the site is, and the reason it was selected is because it's very much like the like Mars in terms of its geological geomorphology, the structure of the area, and sort of desert, because Mars is a desert planet. There is no water except a small amount at the poles, along with frozen carbon dioxide. Now, in fact, this is a photograph from the surface of Mars by one of the Marslanders, and this is at the same level of the camera, a photograph of the area in Utah where the MDRS is set up. So you can see that there is a very similar geomorphology, geologic structure, and so forth. Making it very interesting. This is our crew badge. It's circular, so a few of the names, like mine, is inverted, but and this is McCall. He did our astronomy. Diego Urbana, he was the biologist. Norwick was the health and human services individual, and Saramani, he multifaceted, but he took care of the engineering and again helped with many of the research tasks. This is some pictures of the crew. This is myself, and we're being photographed, obviously, and this is Laskin Saramani, and he is vice president of a biological firm that deals with things such as heart valves and things of that sort. So we would call it biomechanics. He also has a repertoire of very interesting achievements himself, other than being the vice president of research and development for the company that he's with. He also summited Mount Kilimanjaro in Africa. So quite an interesting individual. This is Paul McCall. He was our astronomer. He's from the Florida International University, and he was also a starting quarterback for the university at that time. Now you have to keep in mind that this was back in 2010, so many of our appearances have changed a bit, and some of our bios and resumes have changed a bit. This is Diego Urbano, who did our biological experiments and operated what is termed the green hab, which is where these biological elements were tested and grown. In fact, we were even offered to eat some of them. I'm a vegan myself, so I indulged. Not everyone participated. But on Mars, we'll have to be self-sustaining. You can't have cattle or anything of that sort, at least not on the first trip. It will have to be something that is grown and is in a system that can reuse biological content and so forth. And the water has to be, of course, maintained, just as it is on the International Space Station. This is Bianca Noack, and she is the health and science and safety officer. And this is David Levine. Now, David Levine is our journalist. He does not have any previous experiences in biomechanics or in astronomy or astrobiology or any of that, but he is an excellent journalist. And in fact, he's written a lot of science fiction that he's received awards for. So we elected him we chose him as our journalist and biographer. This is the habitat, and you can see that it has an airlock here. You can't actually see the airlock. I'll get to that in a bit. And it is operated such that everything is just as it would be on Mars. In other words, there's an airlock behind here and a light that comes on saying that the atmosphere has been evacuated and it is okay to open the door. It is simulation, so we didn't actually evacuate the atmosphere, but the time that it would take to do that was an analog of what the actual station set up on Mars would operate under those parameters. What you see on the adjacent hillside is the Musk Observatory, which has a 14-inch Celestron telescope that we use for astrophotography. And this is where we live. Now, there are two stories to this, two layers. The bottom layer is the scientific layer, and it's where the spacesuits are changed and kept, and so on and so forth. Also, the hygiene facilities are on the bottom floor. We call this the science deck. In the second deck, going up the staircase, we have what we would call the living quarters. They're not very hospitable. They're very cramped, but again, when we go to Mars, it's not going to be the Holiday Inn. It's going to be very well. Let me just say that the amenities will be very sparse. The cooking and preparation of the meals is on the second floor. The communication with what would be Earth in a true Mars operation. All of the tasks are done on the second floor. I have a photograph of that in just a moment. The water is recycled, but we also had water. They did not insist that we drink the recycled water, but it was used for hygiene purposes. The water was put through filters, sand filters, and activated carbon filters, and also went into a sort of a pond in the green habitat, where duckweed and various other plants purified the water before it was sent back to the containment vessels for the habitat. But again, we were not, we could have, but no one elected, and they did not insist on us drinking the water, although we certainly could have. They do on the International Space Station. But we did use it for hygiene purposes. Now, the diameter of this facility is exactly the diameter of the Saturn V rocket first stage booster. The reason for that is because NASA has used a similar facility in what was called early on Skylab before the International Space Station. And it was one of the sections of the Saturn V rocket that had living facilities that orbited in space until it was abandoned in favor of the International Space Station. And of course, it burnt up on re-entry from atmospheric drag. And so that's why the diameter is the same. It's because they've already experimented, NASA has, in the Skylab with something of similar dimensions. This is one of our crew, Lashkin, who is standing outside of the airlock on the porch of the HAB, as we call it, short for habitat. And this is in the upper stage, the upper floor, you might say, of the habitat. And there are portholes that look out upon the Utah desert. And I'm doing the commander report here. This is me, 12 years ago. This is our journalist. He's typing up some of the happenings of the day, and so this is what the upper floor looks like. A few reference books in terms of how to operate the various mechanics of the facility. There's also the resting areas. We might say there's sleeping berths. Each one had a private, there's 6 of them, and there's 6 crew members. Each had a private sleeping area that one could shut the door on, but it was very cramped. And one would lift their bunk so they had more room and lower it in order to sleep with minimal comforts. This is also an area where we prepare our foods. You don't see it here, but that's what we do. Now this is a little step ladder over here because you can't see it here, but there's a little storage deck where the dried foods are kept, and then we reconstitute them with water and prepare our foods. Now, again, we were part of a food study for the International Space Station, so we had to say exactly what recipes we used, what we thought about the food, how palatable the dried foods were. We had a limited number of MREs, meals ready to eat, which were military grade. And so that's what went on in the upper floor of the habitat. The lower floor is a scientific deck, and that's where we have microscopes and so forth to evaluate the findings, meteoric findings, and paleontological, micropaleontological formations about the size of a grain of sand. And but it's life nonetheless. So we were looking for prokaryotic and eukaryotic fossilized life forms and inspecting them under the microscope. Now I did identify a foraminifera, which most microbiologists or micropaleontologists, I should say, classify as forams. Radiolaria is another type of microscopic fossil, and Ostracodia, or what they're still around today, they're called ostracods, but they don't preserve well in the fossil record. But we look for those. Occasionally you can find them. This is a short slide about our research domains. Now this is me up here because I was the geologist, paleontologist, looking for microfossils in the upper Jurassic, lower Cretaceous geologic forms, which we took samples. And we also denoted where we got the samples. Taking samples is no good if you don't also indicate where the sample originated, because life might not be widespread on Mars. It may be localized to a very small area. So it's important that notes are kept. And we can see the strata here, various strata, sedimentary rock. meaning that it was laid down when the Earth over Utah had a shallow sea during this period of time, and the life forms settled out and formed limestone and aggregates. This is the spacesuit ergonomics. We were in full simulation here. And this is me squatting down here, making some notes. I was the commander. And so that was one thing we also wanted to discover in spacesuits. How well can you operate a pen and paper? And what sort of ergonomic issues should be reported. All right, the other interesting thing that we did on the mission was to resurrect a radio telescope that we used to tune in as Jupiter passed over the sky. Of course, Jupiter is stationary in orbit, but as the Earth rotates, the constellations and the planets, of course, tend to move in the sky, even though they're stationary because the Earth is rotating. So whenever Jupiter arose, so that we could get the radio signal from it, we received the radio signal, and we used software to plot the various spikes and so forth in the microwaves that were generated by Jupiter. Now, Jupiter is very radioactive. I don't mean radioactive in the sense of nuclear radiation. Radioactive means that it is putting out radio signals, and there's a great deal of atmospheric lightning strikes and so forth on Jupiter. And we recorded those with the radio telescope. How often do these strikes occur? What is the intensity of the radio profile that is being produced by Jupiter as it passes over us in the sky as the Earth rotates? Jupiter is relatively stationary in orbit. It orbits the sun, but it does not move very much in terms of our planet, which orbits the sun at 18.5 miles per second. And Mars orbits the sun at 14.5 miles per second. So the further the planets get out, the slower their motion in orbit. That has to do with Kepler's 3 laws of planetary motion. And the first of which is that all planets have elliptical orbits, which means that they don't have a perfectly circular orbit going around the sun. And sometimes the planet in its orbit might be closer or further from the sun because it's elliptical. Now that's important with respect to Mars. I'll talk more about that in a moment. This is an experiment that involved a particular plant that NASA and our biologist, Diego Urbana, felt would be appropriate for harvesting from Mars. In other words, we plant it there. It grows in the dim light of Mars sunlight, and it creates a berry that is edible, although the plant itself is poisonous. It's known as P. purpurina, and so he did some successful experiments with that. Now this is in the green hab, which is a separate habitat attached to, by a tunnel, the main habitat. The tunnel itself is a simulation. It's not an actual tunnel, but it is a simulation of a tunnel going to the green hab, where these experiments that you see here labeled were conducted and reported. All of this is information and experiments that were reported to the JSC, Johnson Space Center in Houston, Texas, and NASA Ames Research Laboratory in California, along with the JSP, the Jet Propulsion Laboratory in Pasadena, California, part of Caltech. So we had separate research endeavors. Each one of them were documented and sent to the appropriate agency that sponsored the experiments. This is what it looks like. We're in spacesuits here. And I believe I'm number 2, but I might be number 6. It was all documented, but I don't have that documentation with me as to who had what suit on at a certain point in time. I know I was in the photograph, so I'm one of the 2. This is looking out from a precipice, a butte, as they're sometimes called, in the vicinity of the HAB. And you can see it's very rough and deserty. There are no structures other than the habitat itself and the Musk Observatory and the Green HAB and our radio telescope. The idea is Mars, it looks like this. And so if we can operate in this environment ergonomically, then probably, with all likelihood, on Mars, the same situation presenting itself, we have learned how to accommodate that Martian, which would be a habitat on Mars. Very similar, but not quite the same. We have a relatively dense atmosphere on Earth, and we don't have to wear spacesuits here. We would have to on Mars because if we were exposed to the atmosphere, notwithstanding the temperatures and the lack of oxygen, it's almost 100% carbon dioxide, whereas Earth is 21% oxygen, and the rest is mostly nitrogen, with a few of the other gases such as argon, carbon dioxide, and some others. But Mars is almost 100% carbon dioxide, so you couldn't breathe it even if you had the pressure, the atmospheric pressure. But because you don't have the atmospheric pressure without the spacesuits, not only would you not be able to breathe, but your blood would boil because at atmospheric pressure, of course, water here on Earth boils at 212 degrees Fahrenheit. Or 100 degrees centigrade. But on Mars, the body temperature would be enough because of the lack of atmospheric pressure to boil the blood within your body. So it's very important that these spacesuit studies, not only for ergonomics, but also comfort, which would be an ergonomic, and how well we can accommodate the environment within these suits. All right, this is the last of the pictures. This is myself. I'm the commander. I have my my NASA attire, and this is our health and science and officer, and our astronomer, our biologist, Urbano Diego, who also was selected for the Mars 500, which was sealing 6 individuals in a spaceship analog for 526 days, primarily to look at human factors and how well psychologically they could accommodate that lengthy trip. So this is Lashkin. Lashkin was one of our science officers and also our principal engineer. He has, I think, 5 master's degrees in engineering and in other disciplines, and quite a all of these individuals they either have doctorates, she has a doctorate, or they have multiple multiple graduate degrees, Master of Science. The journalist did not have scientific degrees, but he had quite a repertoire of publications, and so he was chosen as our journalist. All right, I want to show you a little more about Mars from NASA, and so I'm going to go to that for the sake of time here, and I'll cover as much as we have time to cover. This, of course, the individual that I pointed out to you, Diego Urbana. This is the Mars 500. It's called Mars 500. It's longer than 500 days, but and this is a habitat that they would occupy for that length of time. It was in Moscow, and it was a joint operation by Moscow and the ESA, which is the European Space Agency, which is the European version of NASA. And so the ESA and NASA worked with us on our experiments, and this one is where Diego joined a different team that was sealed in this vessel you see behind them for 526 days. And I've stayed in communication with my crew members, and Diego is also on LinkedIn. If you want to send him some correspondence, you may do so through LinkedIn. And so let me visit another interesting feature here, and that is information about the planet Mars. All right, now here is Mars. Let me see if I can move this down or up a little bit. There we go. And this is on a website. It's operated by NASA, which is, if you want to get to it, it's mars.nasa.gov. All right, we can post those. All right, and so here's Mars in rotation. And incidentally, Mars has a little longer than a 24-hour day. Our day is just 4 minutes short of 24 hours. So there's a lot of similarity, and thus the interest in Mars for eventual, possibly, human habitation, but that would take quite a bit of time. One would have to build environmentally sealed units and so forth to maintain Earth pressure and such as that. And you would have to have green habs to grow because the atmospheric pressure is not sufficient to simply just move a habitation from Earth to Mars. I'll put it in a little larger perspective here, and I'll point out a few interesting things on the surface. All right, now this is the largest known volcano in the solar system. It is taller than Mount Everest, and it has a proportion as large or even larger than the state of Texas. So let me zoom into this if I can get it to freeze up here for a moment. And it is known as, this is known as what is Mount Olympus, but it has a slightly different name. It is called Olympus Mons, and it is the largest volcanic cone in the solar system. It's on Mars. There are other volcanoes as well on Mars, as you can see, with smaller cinder cones, as you can see here. It did freeze here for a moment. Here's one, here's another, and here's one over here. Now, incidentally, the largest canyon on Earth is right here. Let me getting it out of range here. This is known as Valles Marineris. It was named after the Mariner spacecrafts that first photographed it, and it is known as Valles Marineris. How big is it? Well, it's this is it right here. It is, and these are lava beds, and it goes for 2,000 miles. All right, it's the largest known canyon system in the solar system. All right, so many features, very interesting on planet Mars. And therefore, it's of great interest to the scientific community to go there. This is the ice cap of Mars, mostly frozen carbon dioxide with frozen water as well. It's about, it's very thick. It's about 10 miles thick, or possibly more. Now, they have speculated that there may be a permafrost under the surface of Mars because it was once covered by a lot of water. We know that because we have found hematite crystals, which only form in water, and we found valleys that were obviously carved by running water. So Mars had a more pleasant atmosphere at one time, and so what happened to the atmosphere? What happened to the water? Well, on the Earth, we have what is known as a magnetosphere, generated by the rotation of the outer core of the Earth, which is an iron core. That makes the compasses point north, relatively north, and but on Mars there is no there is no magnetosphere, and it is because the core is not is probably only minimally active. You can see at one time is very active because of the volcanoes. But what happened to the atmosphere, astronomers believe, was since it lost its magnetosphere, there's nothing to protect it from the solar wind. And so over time, the solar wind blew away the atmosphere of Mars to the extent that it is now, which is only less than 1% that of Earth. And therefore, since you remember I said at room temperature, things boil on Mars because of the lack of atmospheric pressure, the oceans and the water boiled away, except for some that's trapped at the poles. Now, there is, of course, a summer and a winter on Mars, just as there is on Earth, because what causes the changes in climate on the Earth is the tilt of the Earth from the vertical of 23.5 degrees, making the northern hemisphere face the sun in facing the more facing the sun in the summertime than the winter time, of course. And the same is true of Mars. At 24 degrees tilted from the vertical, it also experiences seasons, although they're nothing like the seasons of Earth. In winter, temperatures can drop well below 180 degrees minus. And the highest temperature ever experienced on Mars at the base of the Valles Marineris, that long canyon that I showed you, is about 80, I think the highest was 87 degrees Fahrenheit positive. All right, and so this is Mars, and this is where we're going or plan to go in 2033. And so a more detailed look at the surface. You see volcanoes here and there. So it is no longer geologically active as far as we can tell. We have put geophones on the surface of Mars. They measure earthquakes, which we call Mars quakes. And we don't see that. And so it is geologically relatively inactive. There is Olympus Mons, the largest volcano in the solar system. All right, other planets, the moons of other planets particularly have volcanic activity as well, such as Io that has sulfur volcanoes and so on. But the volcanoes of Mars are no longer active. Okay, so quickly, I'm going to in the remaining few minutes, I'm going to give you a little bit of information. Here is the relative size of the Earth as compared to Mars. Mars is about half the size of the Earth, a little larger than half the size. Here are some specifications in terms of the gravitation. The diameter of the planet's Earth is 7,926 miles in diameter. If you drilled all the way through the Earth at the equator, it would be that distance. On Mars, however, it's 4,220. Now, since gravity is based upon the density of the planetary body, the mass of the body, if you will, Mars has less mass, so it only has 38% of the gravity that we experience on Earth. So when one would go to Mars, then you would be quite a bit lighter, except that it'd probably be compensated. The difference would be compensated by all of the equipment, the life-sustaining equipment that you would have to carry on the spacesuit, which incidentally are called environmental suits. The moon has 1/4 the gravity of the Earth and is about half the size of Mars in terms of diameter. All right, here's Valles Marineris, that long canyon on Mars, 2,000 miles long. Here are the moons of Mars. They're very small. This one is only, about 18 miles in diameter. And this one, which is called Deimos, is only about 7 miles in diameter. And they're called Phobos, the big one, and Deimos. Why? Because Mars is named after the god of war, which was Mars in the Greek. It's known as Ares, and so Mars is Ares. In both cases, it's the god of war. Why the god of war? Because they saw that it moved against the sky, and it was red. Mars is red because it has an iron, basically what we would call rust, iron oxide predominant regolith. Regolith is the upper layer of the planet. So these two orbit, and they are named Phobos, which is where we get phobia, meaning fear, and Deimos, which means dread. Okay, so the god of war, Mars, pseudo god, obviously, is orbited by these two, fear and dread. All right, and they're probably captured asteroids. They probably did not form as the terrestrial planets form: Mercury, Venus, Earth, and Mars.
And Dr. Wheeler, may I interrupt a moment?
Sure.
Would you be able to show us your spreadsheet related to the food research you were doing before we take a few questions here?
Okay, yes, indeed. Let me go to the spreadsheet. This is our food study, and there quite a bit here, so I don't have sufficient time to cover it all. But again, I'll be glad to zip all of this up if you're interested and send it to you. It's not anything that can't be shared. And then of course we have some other things. This is when we returned. This is a newspaper article about my research there for NASA, and they took a picture of me. They said they couldn't see me because of the reflection through the space helmet, so they had me take it off. You couldn't do that on Mars, but this is on Earth, so I could remove my helmet. And this is an article about the adventure. I call it an adventure. It was a scientific endeavor, but nonetheless, I have to admit I had a little fun there. All right, and this is a picture of some of the activities that we did. Here's a larger picture of the habitat, and this is a sort of an aggregate of some of the things that that you've seen in the presentation. All right, also quickly, let's see, because I've run out of time, I will take questions on anything that you would like to ask. Sandy,
Yes.
I turn it back to you.
We have a few questions here, and thank you very much. This was really interesting, and I think we could probably talk about this all afternoon, to be honest. But unfortunately, we are on Earth time, and here we are. So there's a couple of questions about becoming a member of the crew. So one would be, is what inspired you to apply to be on the crew, and what is the selection process like? And then the follow-up is, are there any physical requirements or restrictions in order to apply to be on a crew like this?
Well, in terms of the physical, yes, we had to be in top physical shape, as would an astronaut if you had applied through NASA for the astronaut program, which incidentally I applied several times. And one time I was in the short list and almost, and then the shuttle disaster happened, so they froze the operation. However, this did eventuate, and so I got to participate in simulation, what I missed in going up in the rocket. All right. Physical, yes, you have to be in great physical shape. They cannot take the risk of putting you in this sort of environment if you are not in excellent shape, which they do test you for your physical ability to ambulate and move about without the aid of support devices and so on. Now, with regard to how do you apply? Well, you don't apply directly through NASA. You can apply to the research center, which is NASA Ames, that actually conducted the experiments here in the Utah desert at MDRS. MDRS stands for Mars Desert Research Station. That's what this is right here. And so how do you apply? Well, I'm not sure that that this is ongoing any longer. These are archive files back from 2010. NASA, of course, operates in terms of budget, and there's only so long that some of these experiments go. They operate two stations. One is here in the Utah desert. The other is in above the Arctic Circle on Devon Island, which is called FMARS or Flashline Mars. You can Google it. MARS is an acronym standing for Mars Arctic Research Station in the case of Flashline Mars. And this is MDRS right here in Utah, which stands for Mars Desert Research Station, as you can see up here. So how do you apply? Well, again, you could apply through Ames, or you could apply through the Mars Society that jointly operates this facility with NASA. And I would suggest the easiest approach would be to apply through the Mars Society. However, in either case, you have to present a proposal for research. And you have to, of course, understand the research interests of NASA. So you would, first of all, look at that. And then you would make an application consisting of a proposal that you would write up. I wrote a proposal on micropaleontology research involving foraminifera, ostracodia, and radiolaria. Radiolarian are a type of microscopic fossils, along with forams, foraminifera, and ostracodia, which are ostracods. They're still in the ocean, incidentally, ostracods, but they don't preserve well because they're soft-bodied. But at any rate, that's what I was looking for. I did find in my research, I found and documented a new variety of foraminifera. There are probably millions of different varieties. Only a few of them have been documented. All right. I
Maybe we
hope
have time.
that answered the question.
I believe so. I hope so. And Adam, I see, posted a link in the chat to Ames, should anybody be interested in attempting to do something similar, which would be really exciting. And then Tyler has a question. He says, is NASA still planning to use the moon as a staging point for the Mars mission? And if so, do you think we'd have a permanent presence there? Would this open up a possibility for missions to other places in the solar system?
Yes, that is called Mission Orion. And the first stage is to set up a similar habitat on the moon. Now, the reason for that is not only it's a good experimental environment for what we would do eventually on Mars, but it is also a very good place for us to establish some sort of launch facility, because in order to escape Earth's gravity and atmosphere, we have to attain a velocity of 7 miles per second. And that requires a lot of chemical fuel and a multi-stage rocket. However, if we launch from the moon that has only 1/4 the gravity of Earth and no atmosphere, we could launch with probably a single stage rocket. And so for that reason, Project Orion is still actively pursued by NASA. And they are, as far as I know, looking for someone to apply to the astronaut corps to join a mission, that mission or similar missions. But you'd have to apply through NASA directly for that. And their agency for applying is in the JSC, Johnson Space Center in Houston, Texas, right outside of Houston in Clear Lake City on El Camino Real Boulevard, which goes right to the JSC there. And there is the astronaut office. I have framed some of my applications and NASA's responses to me concerning them, because it was kind of cool to be on the short list and have NASA responding to me, even though I think I was on the chosen list, but we had the disaster with Challenger and then Columbia that slowed things down. All right.
I wonder if they're going to receive a flurry of applications, and there might be several of us who receive rejection letters that we will frame now.
Right. Well, I did receive a rejection letter. In fact, I received one that said, "You've waited Dr. Wheeler, we know you've waited a long time to hear back from us, but we have you on basically in so many words, we have you on the short list, and we're going to be calling you for personal interviews and so on." But that didn't eventuate because of the fact that we had the space shuttle disaster, which put things on a freeze for a fair duration. But yeah, so that would be interesting to apply. I would imagine that certainly they choose these people from somewhere, usually academics, or they used to be mostly fighter pilots and test pilots and so on, because they could withstand the G-force of takeoff, although they found out that's not that important. And you don't have to be a jet fighter pilot that can withstand nine Gs in order to be qualified as in the astronaut corps.
That's amazing. Well, we want to thank you for your time this afternoon, and I really do think we could talk quite a bit longer. But thank you. This was a really interesting presentation. And in the chat, I will drop the links for both of our YouTube archives for all of our lecture series. So if you'd like to share this conversation with somebody who wasn't able to attend, it'll be posted there shortly. And then also, if you have further questions or want to talk with Dr. Wheeler about somehow joining the astronaut training program or the application process or grant writing cycle, anything related to Mars, you can reach out to him on the LinkedIn in the link here on the chat. So thank you everybody for your afternoon and your time. And thank you, Dr. Wheeler. This was really, really interesting and fun.
Thank you. Appreciate it.
Great. Well, thank you all. And that'll be it for today. And we will post more series coming up soon.